So we've talked about different types of energy, and some were called kinetic energy and some were called potential energy. But when we go and we want to put it all together and see how everything affects each other as things start to move, what we want to do is we want to talk about certain types of forces which are related to energy. So there are certain types of forces, and they're called conservative forces. So our conservative forces are the type of forces that if we try to store up energy using conservative forces, then or whenever we're using energy with conservative forces, the energy will be stored up and can be used later on. So gravitational potential energy. If I took anything and I lift it up, I take something and lift it up, well, when I've lifted it up and then I'm about to let it go, all of the stored up gravitational potential energy will be returned to the system, and as I let it go, the system will start to fall and it'll move faster and faster. So the kinetic energy will increase because this thing here is called a conservative force, so we can conserve all the energy that was used with this force, and it can be used and turned into a different type of energy later. Elastic forces, we talked about the idea of a spring, and we talked about compressing a spring. If I compress a spring, then I'm doing work on it and I'm compressing it, but later on something's going to be on that spring most likely. We talked about pinball. We talked about a person being shot out of a cannon in a circus. So when those people, or that pinball, starts moving where it originally wasn't moving, it gets all of its energy, all of its motion energy, its kinetic energy, from the idea that we had stored up. All the energy that we had given the system, we had stored it up in the spring. So elastic potential energy, it's called a conservative force. So the force is used when we push in an elastic. This doesn't come up until later on in another course. This is called the electric potential energy. That's also stored up. And so we have a different type also. So over here we have something called non-conservative forces. So the non-conservative forces are the type of forces that when we use them with energy, the energy just basically it's not conserved. Okay, so for instance, if we were to push something along the ground and friction was involved, we would be pushing it, and the friction would be taking awful lot of energy out of it. So we couldn't look at a before and an after case and say all the energy was conserved, because friction is going to be the type of force that's going to take energy out of it. Same thing with air resistance. Air resistance is going to take energy out of the system. So if I drop a ball with air in it, the air will start to take the energy out of the system as the ball is falling, the air resistance. If I have tension in a cord, if I have a box that's just sitting there on the floor, it's not moving, and I tie a rope to it and I pull the rope, I can't really compare the energy before and after the situation, before the pull and after the pull, because they'll be different, because you see the tension in the rope is going to put some energy into the system. Here I have an applied force. So the applied force by people, again, I could be the person pulling on that cord, and I would be putting energy into the system. Okay, and there's something else called the force done by engines or motors or things. All of these things are called non-conservative forces. Some of them are going to be taking energy out of the system. Other ones are going to be putting energy into the system. But what we want to look at is this case where we have we want to compare the energy before and after a certain situation. So if something's going to be moving, we want to try to look at how it's moving, a before and an after case. And if we can, we'll focus on this idea called conservative forces and non-conservative forces. So this is just a list that's in your book. There's something called mechanical energy, and mechanical energy is the sum of all the different types of energies involved. So in so far what we've been exposed to, we've learned about kinetic energy, the energy of motion, and we've also talked about potential energy, which is stored energy in something. We've talked about two different types of potential energy. We've talked about kinetic potential energy, and we've talked about elastic potential energy. So what I'm writing here is mechanical energy. They simplify it with just this capital letter E. So when you see a capital letter E, it's talking about the energy, maybe the total energy of the system. And it's the sum of all the energy. So it's the sum of the kinetic energy plus all the potential energies, plural. So if we have if we had a spring going to be launching a pinball, and the pinball machine is at a slight angle. Well, as the spring compresses and holds the pinball, there would be elastic potential energy involved with the situation. And then later, when the pinball is now removed from the spring and is shot across the game, it's usually going up at a higher elevation. So as it gets higher, it would have a gravitational potential energy involved. So the total mechanical energy at any one particular moment, we would look at the sum of all of these energies that we know about. In an earlier lecture, I talked about something called the work energy principle, where I basically said that the work net being done would equal the change in the kinetic energy, basically. But if I just write this here, and I say the work net equals the change in all of the energies, because it's plural, then I could expand it and say the work net would equal delta KE plus delta PE. And when we're talking about the non-conservative forces, the total work that's being done on a system altogether would end up to be 0. Okay, so when we're moving something using only the conservative forces, the net work being done on the object would end up being 0. The total net work would be 0. Okay, so if I change this and just say it equals 0, and then what I could do is I could expand this again, and I could say this equals, well, what is delta? What does the triangle mean? It means delta kinetic energy. So it would be the final. So it would be this. It would be kinetic energy final minus kinetic energy initial plus, and again I'll expand this piece here, delta potential energy. I'll say it would be the potential energy final minus the potential energy initial. And if I take those negative, these pieces, which has a negative kinetic energy and a minus potential energy, if I bring them to the other side, so if I add that to both sides, what I'll get is this, that the kinetic energy initial, this initial is usually written, in some classes it's written with an I, in most classes it's written with an O, so sorry about that. So if I bring this kinetic energy initial to the other side, it'll become plus kinetic energy initial, plus bring this potential energy initial to the other side, add PE initial to both sides, and I'll get plus PE initial, and then that's equal to kinetic energy final plus potential energy final. And this is the general form here for something called conservation of mechanical energy for conservative forces. So what we're saying is, if we pretend that there's no air resistance and that there's no friction, that there's nobody pushing on something, there's nobody pulling on something, then if we take any object at all, we could take a ball, we could hold it up high, we could let it go. So if we did that, when we let it go, at the beginning, it could have these two types of energy. The example I just gave, it didn't. It wasn't moving, so it would have no kinetic energy. But you would look at the situation at the beginning, and then you would look at the situation at the end, when it's about to hit the ground or something, and you would see, how did the total mechanical energy at the beginning equal the total mechanical energy at the end? And when we say conservation, we mean that it can all be accounted for. So all of those two mechanical energies at the beginning have to equal all of those two mechanical energies at the end. One will go down and one will go up. So as it's very, very high up, it'll have a lot of potential energy. But at the bottom, when it gets to the bottom, it'll have no potential energy, gravitational. So the potential energy will be going down, and the kinetic energy will do the opposite. The kinetic energy will be going up. So way at the top, it's not moving, so there's no motion energy. And when it gets to the bottom, it's moving faster, 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 faster. So it has an awful lot of kinetic energy at the bottom. This is an example of conservation of energy using non-conservative forces. What it says is, I'm going to drop a ball off a 20-meter tall building. It says find its speed when it is 10 meters above the ground, and then it says in part B, find its speed when it's about to hit the ground. And over here it says ignore air resistance. So by saying ignore air resistance, we're pretending that this is something called conservative forces only. So we will, simplify things a little bit. So if I write out the formula basically says for non-conservative forces that the total initial energy will equal the total final energy. And if I expand upon that, that would be the kinetic energy at the beginning plus the potential energy at the beginning equals the kinetic energy at the end plus the potential energy at the end. Okay. So this is the idea of conservation of mechanical energy. And if I keep on expanding that, it would be, well, kinetic energy expands to 1/2 mv initial squared plus m times g times h initial, sorry, this is a y. So we're talking about gravitational potential energy, and that equals 1/2 mv final squared plus m times g times y final. So that particular problem there can be solved by taking, in this formula on the last line here, this is called conservation of energy for conservative forces only. So we're pretending that all the forces and all the energy can be accounted for. So if you notice, they did not give us a mass in this problem, and that is okay because the mass is in every single term. So we can divide every single term by m, and if I do that, I'm basically going to cancel out the m. So if I divide every term by m, the m's are going away. Okay? And now I can start plugging in. And you may notice that if I drop a ball, okay, if I just hold a ball in the air and then I drop it, that the beginning speed of the ball would be 0. So this term right here would be 0 meters per second. So this whole term cancels out. And it says that we're going to drop this ball, and we want to know what it is when it's 10 meters above the ground. So I'm just going to physically plug in the numbers exactly as I see them. G is gravity, 9.8. So it's 9.8 meters per second squared times the initial height. It was 20 meters off the ground. Equals, I have 1/2 here, so I'll put 1/2. V final is what I want. Plus, and then I have gravity here is 9.8. And over here I'll put the height. I'm ending at 10 meters above the ground, so I'll put 10 here. So when I just plug this whole thing in, this becomes, take your calculator out, this becomes 196. This becomes 1/2 V final, which is squared, and this here becomes 98. So you just have to solve this for V final. So if I subtract 98 from both sides, I'll get 98. Multiply both sides by 2, and then take the square root of both sides. So I'm going to get a final answer of, for part A, V final is 14 meters per second. Okay. So I did that math out, and over here I'm saying for part A, V final comes out to be 14 meters per second. That's a scalar. Scalar means that there's no direction associated with it. So yes, velocity is a vector, but this chapter deals with scalar numbers. So we're talking about this thing is falling, and it's falling with a speed of 14 meters per second when it's at a height of 10 meters above the ground. Let's try part B. Part B tells us that it's the same thing. We're dropping the ball from a height of 20 meters above the ground, and we want to see how fast is it going just when it's about to hit the ground. So it starts the same. This ball is not moving at the beginning, so it'll be 1/2 mass times velocity initial squared. Well, the velocity initial would be 0. So this thing can go out. And then we'll have the potential energy of it. It's m times g times y. So the mass, let me just write that. It's mass times g times y initial. Okay, and we know the y initial is 20. The kinetic energy final is 1/2 mv final squared. And the potential energy final is m times g times y final. But we know y final. When something gets to the ground, the height above the ground is 0. So I will say that this height right here is 0 meters per second, 0 meters only, it's a height. So this whole term cancels out. So now we're looking at these two, mgy and 1/2 mv final squared. I can cancel out the m's because the m's are in every single term involved. So when I plug this in, it comes out to be G is 9.8, Y initial is 20 meters, equals 1/2 V final, which is squared, which you're trying to solve for. So to solve for that, basically, these two multiplied by each other is 196. So you would multiply both sides by 2, and then you would take the square root of both sides to get V by itself. And when you do that, the number comes out to be once again, the number comes out to be 19.6. I'm sorry, 19.8. But it's a scalar, and once again, it's not going to be a negative number. We know for a fact the velocity while it's going down is a negative number, but this thing here is a scalar, so it's only giving us the magnitude. It won't give us the negative piece of it. So what I failed to do, what I should have done right away, is I like to draw these pictures usually. So you see there's a ball up here, and that's where we're starting. And this building is 20 meters tall. But we're going to end, for part A, we're going to end right here. And that's going to be 10 meters above the ground. So this is where the ball is ending. So I usually like to do this and put the picture, and right near the picture, it's helpful if you can write the initial conditions that you know about. So for instance, if I could possibly write V initial, and I could write H initial. So V initial was 0 meters per second, and H initial was 20 meters. And then over here, this particular one, I could write V final. So here, V final came out to be unknown, and H final came out to be 10 meters. Okay. So if you take the time to draw the picture and put the starting and the ending points, and then you can put the original conditions, so you know it's much easier to just plug it into the formula. So for this particular case, we have 0 meters per second, and 20 meters is the height initially. And when we did part A, we ended in the halfway, and we said that this would be a final velocity of unknown, and the initial final velocity of the height was 10 meters. So I usually draw a picture of these things to show how you get them. When we talk about conservation of energy using non-conservative forces, what we're saying is friction is involved, and friction is going to take some of the energy out of the system. We're saying air resistance is involved. Air resistance will be taking energy out of the system. We'll be saying that somebody's pushing on this object or pulling on this object, which is changing the amount of energy at the beginning to the end. So when we say we have non-conservative forces, non-conservative means, so when we say this, we're talking about frictional forces. We're talking about air resistance. We're talking about applied forces. Okay. We're talking about forces from an engine or a motor. We're talking about forces in a string, tension forces. Okay, so if that happens and we're trying to prove conservation of energy, what will happen and we'll see is that the energy initial will in fact not be this. So we'll say the energy initial will not be equal to the energy final. And why not? Because some of the energy is being taken away by friction. That's what friction does. It heats up things, it makes sound, and it takes energy out of the system. That's why we spend so much money trying to perfect cars and trying to get the right oil and things like that in the engines to reduce the amount of friction. Because what a car does, a regular car, the friction and all the internal movements and stuff takes approximately 88% of your energy away. So every dollar you put into the gas tank, approximately 12 cents is helping you move forward, and 88 cents is being wasted. So the way we write this is we would say, just like at the beginning when we did the work energy principle, we would say the work done by non-conservative forces would equal the change in the energy. Remember, that capital letter E means mechanical energy. Okay, so if I had to expand this, mechanical energy would be this. It would be the final energy minus the initial energy. Okay? Now, whenever I talk about energy, I'm talking about, mechanical energy. It's kinetic plus potential. So if I expand this thing here, well, let me just expand it one at a time. So the work non-conservative will equal, and this becomes 1/2 mv final squared plus m times g times y final minus 1/2 mv initial squared minus mgy final initial. Okay. So this is the idea here. What I'm saying is the work non-conservative would equal, there's the final kinetic energy. Here's the final potential energy, gravitational. And then I'm going to subtract away because I have to minus all of the types of initial energy. So I'm minusing away my initial kinetic type of energy, and I also have to minus away my initial gravitational potential energy. Some people think that I should have a plus there, but it's really, I'm minusing with parentheses, I'm minusing everything that would be in here. So when I talk about the total energy, I would have kinetic plus potential, but I have to subtract away both of them. So this is the formula right here that you would use for conservation of energy with non-conservative forces. And if I may, I'll just take one change. I'll change this. What does work equal? Well, you see, work equals a force. We're talking about the non-conservative work, so it's the non-conservative force. That's what the NC means. And work is a force times a distance, so this is the distance the object will be moving through. And here, I ran out of room, so I'm just going to squish in. This is the cosine of the angle. And that's the angle. If you remember when we did work at the beginning of this chapter, that's the angle between the direction that the object is moving compared to the direction that this particular force here would be pointing. Okay. Here's a sample problem of conservation of mechanical energy using non-conservative forces. So what it says is, I have a ball that is going to be released from rest at the top of a 10-meter tall building, and I'm saying that when the ball is about to hit the ground level, the final speed of the ball is 11.5 meters per second. And the question is, find out how much work the non-conservative, what does it say? It says, calculate the work done by the non-conservative forces. If I use the formula for work being done by non-conservative forces, I have a formula that looks like this. Work, non-conservative, equals delta E. Okay, so I have to do, and I have to expand it. So if I expand it, delta means the change of it. Always means the final minus the initial. So this would be the energy final minus the energy initial. So that's what it equals. And if I expand this, it equals 1/2 mv final squared minus m times g times y final, plus minus 1/2 mv initial squared minus m times g times y initial. Okay. So I just really have to plug this in this case. Now, I'm looking for the work non-conservative. That's what the N and C mean. So in this particular case, my problem is not written perfectly because I need a mass for that particular ball or something. So if I gave that ball a mass, I could say I'm going to drop a, let me just say it's a 0.25 kilogram. Okay. So I'm going to drop, I just changed it. So I'm going to drop a 2.5 kilogram ball off of the 10-meter tall building. So I'm just going to plug all these numbers in. So I'm going to say the work done by the non-conservative forces equals 1/2. The mass of this is 0.25. I plug everything in. So what you see here is the 1/2. The mass of it is 0.25 meters per second. Sorry. The mass of it is 0.25 kilograms. My mistake. The speed of it is 11.5 meters per second, and we have to square that, so you see the squared. And then I'm going to add the final gravitational potential energy, which in this case comes out to be 0, because 0 joules, it's the final height was 0. We were right at the ground level. And then I'm going to say we're going to minus the initial speed. We're going to try to minus 1/2 mv initial squared, but it wasn't moving because we dropped a stationary baseball. So this would be 0 joules. And then we have to say minus, and we have to minus this. So the mass of it is 0.25 kilograms. I'm running out of space once again. So here, I'll put in 9.8 meters per second squared. And my initial height was at 10 meters above the ground. So that goes in there. So I have those pieces now. So this number comes out to be 16.53. And this becomes 24.5 joules. And when I do this, I get 7.97, but a minus. I get minus 7.97 joules. Okay, this is the work being done by the non-conservative force. So does this make sense? I'm going to say it does. We're asking for how much work is being done by something called a non-conservative force. Non-conservative forces are the type of forces which take energy out of the system. So as you can see right here, there's a negative sign, which means the final energy is less than the initial energy. So we didn't have, you see, if it was just we pretended that there weren't any non-conservative forces. If we said air resistance is not involved, then we would have put here that the final energy would equal the initial energy, you see? But it's not the case. We're saying there will be a difference between these two energies, and the difference between those two energies is this number here. So we start, the ball was up very, very high, and it had so much energy involved with it, and then when we let it go and it fell down, it had a certain number of energy at the bottom, but it wasn't the same. The energy at the bottom was less. So what we did is we had to go and we had to subtract these two numbers here, and we got a negative work by non-conservative forces.